So hello everybody, I'm happy to host Koren. Tomer is assistant professor in the School of Computer Science at Tel Aviv University. Previously, he was a senior research scientist at Google Brain. His main interest is in machine learning and optimization, and today he will talk with us about does SGD generalize better? Why does SGD generalize better than others do? So, Tomer, the stage is yours.
Thanks so much.
Thank you.
As I said, it's my first post-COVID talk, live talk. So it's post-COVID already, right? I mean, I'm not sure. It's not clear, right? It seems so. Okay, so what's that? Okay. Yeah, I'm just something flickering in front of me, so I'm looking. Okay. Thanks for the invitation and introduction. Today, I'll talk about joint work with my PhD student of mine, Idan Amir, joint student with Roy Livni and Yair Carmon from our department. I will not get to talk about other works that are mentioned here, but doesn't matter. Okay, so the main topic will be about generalization of SGD and kind of why does it generalize, and I will frame the question as kind of why does it generalize better than some other things. Okay, so that will be kind of the main thing we'll go towards. Okay, so SGD, I guess in this audience and the audience at home needs no introduction. I'm pretty sure. I think by now it's probably the most well-known algorithm in computer science and beyond. Well, much better known than Dijkstra and all the others, right? I mean, yeah. So I'm sure you all know about it. But in any case, just for notation, right? What is a stochastic gradient descent? It will be the main, one of the main kind of objects in this talk. Okay, so we are, it's more general than that, but let's think about a supervised learning task, right? So that we have something in mind. So in a supervised learning task, we have, it's okay that I point on the board, right? They can see the board? Okay, perfect. We have a sample, right? So I will call the data points in the sample Z. So we have Z1 to Zn, n is the sample size. And each Z, just for intuition, right? Just for that we have something in mind, it's kind of a pair of, it's a labeled example, right? It's a pair of some feature vector and labeled, say, CFAR10 image and the corresponding label. And what is SGD? What SGD is doing, it picks, let's say, kind of permutation of the data, right? So it picks some index at time t, it's index IT, picks the corresponding sample data point ZIT, and looks at the loss function defined on this example, right? So F here is a loss function that measures the loss of some predictor, some hypothesis, right? Defined by these parameters W, the loss of this thing on the data point Z, ZIT, and it takes a step according to the gradient on this example, but in this example alone, forgetting for the moment from the full sample, right? Just let's say that we start from 0, okay, without loss of generality for this talk, and it does an update of this form. Eta here is the step size, and we take a gradient with respect to W on the particular example that we picked. I guess this is kind of familiar to everyone, but yeah, just to put notation. Okay, please, of course, just stop me blatantly at any point in time, right? Otherwise, I will not stop. Okay, so why does SGD generalize? So SGD does generalize in many settings, and kind of this is a question that keep kind of coming back, and kind of it's in the main interest of the community over like for years now. And there's a lot of literature. This is just kind of a non-representative sample in kind of there are rigorous works, there are non-rigorous works. There's a lot of interest of why these things generalize in practice and in theory. I guess the most well-known on the more theoretical side, the most well-known paper is the strain faster generalized beta, that kind of maybe kind of one of the earlier papers on this kind of renewed interest in these kind of questions. There are kind of information theoretic perspectives into the thing. All this wide versus sharp minima kind of discussion, and all this inductive bias or implicit bias of algorithms. We will get to some of these things later, and there is some shameless advertisement of one of my own papers on the subject. I will not talk about this paper today. And maybe before we kind of delve into all of this discussion, it's important to say that, okay, the first answer to this question should be, why does it generalize? Okay, there is, in simple cases, there is a very, very simple proof that should convince us that it generalizes. Okay, there are disclaimers, I'll say them afterwards. And let me, it will be illustrative for the rest of the talk that I will kind of show kind of very quickly kind of the proof from the book of how do we show generalization in convex case, in a simple case. Do you show this in kind of the basic ML class here?
We just realized we have no idea.
You have no idea. Yes, I realized that for some, I mean, I was surprised that it is not being seen in many intro to ML classes, and it's kind of, yeah, I don't know, very weird. So maybe some of the audience will learn something new. I hope most of you have seen this thing at some point in time. I'm sure most of you here did see this. Okay, so in the convex case, there is a very, very simple proof, two-liner proof, basically, that shows that this generalizes. Let's just look quickly at it. So we use a stochastic gradient at each point. This is this gradient over a single example. And we are interested in minimizing the test loss. What is the test loss here? It's just the expectation of the loss on a new example drawn from the population data, right? So this is kind of the true objective in generalization, minimizing this expected loss, okay, with respect to W. And SGD does this, right? It takes this stochastic gradient and does this stochastic gradient update. And the only thing that we care about, we can forget about all this sample and all this supervised learning task. All we care about is that the expectation of this stochastic gradient is the true gradient of the true loss function. Okay? This is just linearity of expectation, basically. So conditioned on the random point that I'm querying, the expectation of the gradient is precisely the right gradient. And also the gradient is bounded. It's important. And in most cases, we assume that certainly in the convex case. Okay, so let's see how it goes. So first, the analysis just follows the distance to the optimizer. So W star here is the minimizer of the true loss of this capital F. And we just follow the distance of our iterate to the optimizer, right? So we can, this is just algebra. We can just plug in the expression for WT plus 1 and kind of open the square and do some algebraic manipulations. And we get this. We isolate the dot product of the stochastic gradient with this vector to distance to directed distance to the optimum. And now we can sum this over time, and we have this telescopic terms here that cancel out, and we get this bound. Now, the right-hand side of this bound, if we pick the learning rate correctly, we get like 1 over root t. So right, if I pick eta to be 1 over root t, this becomes 1 over root t, and this becomes order 1 over root t. So everything is 1 over root t. This thing converges to 0. This average converges to 0 at the rate of 1 over root t. Now, here comes maybe the more interesting part of the proof. Now we take expectations, right? And it's like super elementary, but still, it's kind of, I don't know. surprising that it works so easily, right? If we take expectations and we do it carefully, because GT is kind of a fresh random variable, we can just put, instead of GT here, the true gradient, the gradient of the true loss, and here comes the true loss suddenly. And we now use convexity, basically twice convexity, and we get that for the average of the iterates, we get that this thing is lower bounded basically by the excess loss, kind of the suboptimality of our solution compared to the optimum in terms of the true loss, okay, the generalization loss basically. And so we get that this basically combining these two inequalities, we get that this quantity here is bounded by 1 over root t, okay? And so maybe, yeah, just let me say that this is more generally is this online to batch argument. For those of you familiar with online learning, this is kind of a way to convert online guarantees to batch guarantees, to statistical guarantees. Okay. I guess many people, have seen this maybe, but something that surprised me that some people that I talk with don't realize or overlook is this, that it gives guarantee with respect to the true loss. Okay, so many people view SGD as kind of an iterative process on the empirical loss, and kind of overlook the fact that it actually gives it actually operates on the true loss. Okay, so basically it uses stochastic gradients with respect to the true loss, and the empirical loss is never here. There is no empirical loss here in the proof. It's kind of, okay, so surprisingly, I was very surprised that this is not fully realized by people. So this is a very complete analysis. In the convex case, SGD generalizes at the rate of 1 over root. Okay, textbook material. Okay, so here are the disclaimers. So of course, this thing, we used convexity, kind of crucially. And in the non-convex case, things are more complicated. There is some analogous analysis in the non-convex case, but it doesn't give us exactly what we need, what we want. And it has been observed in practice quite a lot in many cases that so non-convex case, there are different minima, not just single one. And different minima have different generalization behavior. So things are a bit more intricate there. So we will see that actually this non-convexity is actually this phenomenon that occurs in non-convex problems actually occurs in convex models as well. So we don't need to go actually to non-convex models to kind of tackle these kind of issues of multiple minima. Convex problems can also have multiple minima. So we'll get to that shortly. And another disclaimer is that this analysis doesn't apply to data reuse, to multiple epochs. I cannot sample the same example twice because I've used this independence assumption between the stochastic gradient and my iterate. So this breaks down when I do kind of multiple passes. And there are actually very few non-trivial things that we can say about multiple passes over the data with respect to the test performance. And this is also going to touch one of the main points of this talk. So these disclaimers are valid, of course, and I'm going to touch on both of those shortly. Okay, so back to the question. We want to kind of understand why SGD generalizes, and I'm going to argue that even in the convex case, there is something to understand. Okay, so even though there is a very simple proof, and you can say, okay, that's it, right? I mean, proof from the book, two-liner. I'm going to argue that there is a bit more to that, and maybe why does this question keep coming back to us? Why there is an issue at all? Why do we need explanations, right? So I'm sure that this thing, I'm sure you know from intro to ML classes. This is something that we do see in intro to ML. Is that the traditional view is what we call what you see is what you get, right? Or in technical terms, uniform convergence. So basically, no matter what the algorithm does, for all possible outputs, the test minus train loss will be small, and therefore it doesn't matter what the algorithm does, it will generalize well, right? So this This is called the kind of uniform convergence, and it takes place both in PAC learning. This is we get like VC dimension bounds. Kind of the VC dimension dictates the rate of uniform convergence there. In generalized linear model, linear regression, logistic regression, and so on and so forth. This is dictated by the Rademacher complexity. There we have pretty good understanding what's going on because we don't care. It doesn't matter what the algorithm does. And therefore, in learning, in this case, it just amounts to empirical risk minimization. So just take the empirical sample, minimize it, and then whatever you get there will generalize well, just depending on the VC dimension or the Rademacher complexity or whatever, right? Or the appropriate dimension. And unfortunately, this doesn't, it isn't quite the case more generally. Okay, so kind of these kind of models are actually kind of very nice in the sense that uniform convergence is really kind of captures learnability, but they are unique in this sense. Okay. So what do I mean exactly by that? By doesn't hold more generally. So we often see cases both in practice and as I'm going to show you also in theory, that often learning is dimension free. Think about optimization, right? In d-dimensional space, it's going to be dimension independent in many cases. Whereas empirical risk minimization or uniform convergence rate will be linear in D. Okay, and basically this is just getting D linear in D rate is trivial, right? Just follow basically from naive kind of covering numbers or epsilon net arguments. Okay, so just because we can cover with exponential in D number of epsilon balls our kind of set of possible W's, we get linear rate. So basically, we can get dimension dependent bounds, but it's not. These are trivial, not interesting, and not especially not interesting because we know how to get dimension free bounds in other ways. Okay, so for those of you who have been following the literature, I'm sure you have some paper in mind, something in the kind of very influential paper and well known. I'm not going to talk about it in this talk. Don't worry. Not yet another talk about rethinking generalization. But we should say that this paper did bring a kind of to the table these kind of questions that uniform convergence fails kind of to, at least in practice, to understand what we're seeing. Okay, so forget the first line, the first bullet here. The main point is that the generalization here is essentially algorithmic dependent. I'm talking about empirical observations for now. Okay, and the main question that kind of this paper mostly asked questions and didn't give many answers. The main questions with respect to what are the properties or aspects of the learning algorithm that govern generalization. Okay, there is no VC dimension that will answer all of our questions. So what properties of the algorithm will, since generalization is algorithm dependent, what in the algorithm, right? What does affect generalization? And one of the main things that came out of this paper is a long line of work on implicit bias of learning algorithms. So trying to understand what kind of implicit regularization or inductive bias learning algorithms induce towards generalizing. Okay, so there's a huge amount of literature coming out of this paper. Okay, actually for SGD and kind of simple optimization algorithms, there is a much earlier paper co-authored by two people from this department in kind of different points in time, at least, with this title, Stochastic Convex Optimization. So it's like 10 years before the rethinking generalization paper. And these guys observed something very interesting. So in the convex setting, Stochastic Convex Optimization, I will shortly define the setting. We have a very interesting phenomena, which basically the same thing that this rethinking generalization phenomena, but in a very simple case. So even in this case, which is much simpler than deep learning, right? In high enough dimension, remember that we want dimension free bound. So let's just take D arbitrarily large. This problem is always learnable using SGD. Okay, basically what we just saw in the earlier slides, but uniform convergence fails to hold. So ERM doesn't hold. It doesn't work. Provably, it fails to work. And therefore, generalization is algorithm dependent, right? ERM won't work in general, so we have to look at the actual algorithm that does this ERM. And I would argue that this is kind of an ideal setting for studying. Before we go to deep learning, right? This is an ideal setting to studying our understanding of generalization. Yeah.
When you're saying the dimension, you mean the parameter dimension.
The parameter dimension, yeah. What other dimension?
The input dimension.
Oh, I see. So
The number of parameters.
there are a number of parameters in W. Yeah, the optimization the dimension, right? Yeah. So my point is that like, this is kind of a very nice kind of a test case for kind of understanding whether we understand, right? Okay, so what is stochastic convex optimization? We've seen this kind of before, but not maybe formally defined. So here is the formal kind of in one slide, formal definitions. So our goal again is to minimize this expected loss when we sample Z is a data point, kind of a test point, right? In the test set, there is an unknown distribution, the kind of the population distribution, data distribution, and we are interested in minimizing this expectation. And here W is a predictor. I'm putting kind of in a kind of quote because it's not a linear predictor. It's a kind of parameters of a predictor. Maybe this is now a convex setting, not a generalized linear model or something. So it's it goes beyond kind of the linear prediction model that we kind of used to think about. And yeah, I said about that. This is kind of a labeled example in supervised learning, and this is our goal. I'll denote it by F, capital F, as before, and we have access to sample from this unknown distribution, IID sample, and I'll denote the empirical risk, which is just kind of the empirical surrogate of this guy in terms of the sample of our observed sample by F sub S. Okay, so we have a sample S, and F sub S is the empirical risk on this sample. Okay, so now let's try to explain why does SGD generalize in stochastic convex optimization. We have a proof, right? But let me say a few words anyhow. So what did this guy guys in this paper earlier paper observe? They said, okay, so this. So basically, there are two optimal algorithms to learn in this case. Okay, uniform convergence fails, but there are two other algorithms that are not just kind of abstract ERM. The first one we know about is SGD, and this was kind of maybe a new understanding at that point in time that SGD is optimal in this case, even though optimization people knew about it way kind of ahead of time. And maybe a new observation to that paper is that also kind of a slightly tweaked ERM will also work. So ERM fails, but regularized ERM will always work. Okay, so what is regularized ERM? Just take the empirical objective, add a strongly convex regularization, like lambda times some square norm, and minimize this. No matter how you minimize this, it will work in terms of generalization. Okay? So two optimal algorithms with pretty much the same guarantees. The analysis is a bit different, but the same guarantees. And the conclusion from this paper, and I would say kind of maybe not just from this paper, but I think this is a very general kind of way to think about things. I, for one, thought about these things this way before I even realized there's this paper. I didn't know about this paper. Before I knew about this paper, is that the key here to generalization, to test performance in this setting, is regularization. Okay? So this is kind of the way they phrase it. The key seems to be regularization rather than the typo is in the source. Procedural online versus global minimization. So it doesn't matter that this is online and this is online minimization and this is global minimization. The key here is regularization. So by the way, why SGD is regularized? How do we see that SGD, where does the regularization comes in SGD? So a very kind of common way to think about gradient methods in general and SGD in particular is kind of that they solve kind of a minimization problem in each step. okay, a regularized minimization problem. So this is equivalent. These two update rules are equivalent. This is very, very well known. And so we can think about SGD as something that injects regularization in each step. Okay, so the key, this is kind of the main takeaway from this paper. The key is regularization. And I still think about these things as basically all of these regularized algorithms are the same. The key is regularization. Okay, so yeah.
I mean, these are
Perfect.
I guess these are problems which are in condition, right? Because their dimension is infinity. So you've got lots of global solutions.
Think about, for simplicity, finite dimension, but arbitrarily large. We don't want to depend on D, okay? But yeah, you can think about infinite dimension if you find it easier, but anyway, but
so you've got lots of global minima, and you want to find one of them, that's optimality?
For this guy, you have only one.
Yeah, I mean, for the first.
The first one, it doesn't, yeah, we don't know. I mean, yeah, but SGD that does kind of, so we know that ERM fails, right? This is a kind of
I'm not just saying what is optimal.
Optimal in the sense of what is the number of examples that I need to sample complexity for finding like epsilon test error, right? I want to minimize the test loss. How many samples do I need from the distribution? Your comment about SGD, that's kind of, it finds, we don't know what minima it converges to, and we know that some of them are bad, right? Because ERM fails, but suddenly, somehow, surprisingly, SGD converges to a good minima. And this is something that kind of mind-boggling, even though we have a proof, right? We have a simple proof, but it's still kind of what's going on. So this is, I'm going to touch on this very shortly and get to the main result like in 2 minutes. Okay, so I would like to phrase this question in the stochastic convex optimization world as kind of, let's try to understand why SGD generalizes. If regularization is really the key thing, let's try to think about, let's compare to other algorithms. Why does it generalize better than others? Okay, so does it generalize better than others? We'll see that it does, and we'll try to understand why. Okay, so basically the question that I'm going to propose, the main question of this talk, is kind of why. Let's compare between SGD and a very, very closely related algorithm GD, which is actually kind of simple, right? There is no stochastic thing. So what is GD? What do I call GD? GD is the batch. So SGD we already seen, right? This is kind of stochastic updates. What is GD or batch GD? It's the same algorithm, same iterative updates, but now we are using the full gradient of the empirical sample. Not we are not picking one example at random and taking the gradient, but just the full gradient of the empirical. So we average all gradients, if you wish. Okay.
You use the same sample twice, right?
Yeah, think about one pass. Okay. The easy case. Yeah. But okay, so here is one thing to note is really that here we use like fresh sample each time, and here we are reusing the data in a sense, right? But this thing does converges to an empirical kind of, does perform very well on the training set at least. So why compare between these two algorithms? So in terms of the regularization, the intrinsic regularization, they are the same, right? I mean, the same implicit regularization is being injected in each step. So if this works, we expect that the other one should work, right? I mean, why, if regularization is key, then they should be the same. And as I just said, as empirical minimizers on the training set, they perform equally well. Okay, so they converge after n steps, as we've seen in the kind of the proof from the book, at the rate of 1/n after n steps. Okay, so after one pass over the data, they get to the statistical optimal rate of 1/√n. This is the best you can do in statistically speaking. Okay, but what about generalization? So they are good, same in terms of regularization, same in terms of empirical error. What about regularization? Generalization, sorry. So for SGD, we already know the right proof from the book tells us that for any, if the loss function is Lifshitz, and for any distribution, doesn't matter. If we pick the step size correctly and do one pass, don't reuse data, then we get this 1 over root n. What about GD? So here is, we get to a new thing. It's going to appear in, I forget, what is it now, Colt? Yeah, Colt. It's going to appear in Colt this year. Kind of a lower bound separating the two algorithms. Okay, so while SGD converges always at the rate of 1 over root n, for GD we know the following. So for sufficiently large dimension, for now we can only say this for a very large dimension exponential in the training sample size, right? But we have good reasons to conjecture that it applies kind of even for much lower dimension. So for any sample size n and sufficiently large d, we can find kind of a learning problem such that GD doesn't generalize at all. Okay, so you run it for n steps exactly like SGD with the same step size 1 over root n. It will optimize the training loss, for the same reason as I said before, for the same reasons that SGD optimizes the training loss, but it will fail to generalize. Okay, so like no generalization, like lower bounded by a constant. Okay, so this is kind of the simplest case of the main result I'm going to present. Let me say maybe one more thing about the more general form of this result, and I'll tell you why I'm showing you this. So we can tell this not just for eta, which is equal to 1 over root n. Okay, we can say this for any learning rate, fixed learning rate that we're going to use. So if you use eta learning rate, your generalization error will be bounded by this sum of two terms. This one is standard from optimization. This is the more interesting, the new thing. And you see that if I plug here 1 over root t, or t equals n, and this is 1 over root n, we get a constant. Okay, so this is kind of the more general result. Why am I showing you this? Is that we get something interesting from this bound, is that if we try to minimize the right-hand side and kind of make it equal to epsilon, we kind of target epsilon accuracy on the test loss. We can make it the right-hand side epsilon by picking eta to be epsilon cubed and t to be epsilon to the minus epsilon to 1 over epsilon to the 4th. Okay, and if we plug in our desired epsilon 1 over root n, we get eta, which is something like 1 over n to the 1.5, and t n squared. Okay, so and then we get epsilon generalization error, and surprisingly, this is optimal. Okay, so we can make GD to work in the sense of sample complexity. We can give a GD n examples and get 1 over root n generalization error, but it will require very weird settings. We need to take a very, very small step size, train slower, not train faster, but train slower, and for more iterations, n squared rather than n. Okay. So surprisingly, this is optimal. There is a matching upper bound based on stability arguments, very recently by a paper by Basili and co-authors. And what we do see here is that, so in sample complexity terms, GD is great, but if we care about number of steps, right, kind of oracle complexity, number of gradients that I'm going to query, GD is going to need quadratically more steps than SGD. Okay, so it's kind of substantially worse in this sense. And one thing to note is that each step of GD is also more expensive than SGD, right? So it's n times more expensive if you think about computing gradients and averaging them, right? So yeah, so GD is not great in this kind of setting. And kind of, yeah, I mean, so regularization, it's not clear whether it's the, at least if we care about number of steps, right? It's not clear if this is kind of the real thing. Questions? Yeah.
But if you take these parameters, then you recover the generalization about the best.
Right.
Right. So it's
sample complexity, you get the optimal result. But you'll need n squared steps of GD.
Yes, it's a more computational expense.
Right. But sample complexity wise, you can make it optimal, but in a very weird it was just been observed very recently, right? It's very weird setting and different analysis, and yeah, very interesting. Surprising. But number of steps, much worse. Questions?
I take GD and just add artificial noise, like people did before SGD.
Yeah, so there's
you'll get SGD results.
Not quite, right? Because the noise in SGD is not coming from just Gaussian noise, but from
So I think artificial noise wouldn't help.
I'm not okay, I don't know the answer, but I don't know of any analysis that shows that. I know of attempts. All of this information theoretic analysis that I mentioned are doing something like that, and they get dimension dependent bounds. So they don't get the even in convex case. Okay, so yeah, I don't know. We don't know, I guess, as far as I know. As far as I know, we don't know. Okay. More questions before I get to some technical details? Not sure I have much time.
Oh, yeah.
Okay.
Is it still in convex setting? Yeah.
Yeah.
Thanks. Okay. Question, mostly we are talking about SGD generalizes better than other with ERM loss, or in a probabilistic perspective, usually MLE loss. Do you think SGD idiosyncratic variational inference will also generalize better, for example, with surrogate loss, such as evidence loss bound, or?
I'm not sure about this stuff. But I'm mostly saying what I know. Things I'm not saying, I probably don't know. And I think that I mean, these are still, as you see, even in the most basic settings, right? I mean, things are still not fully understood, surprisingly. I will be happy to answer offline. I'm not sure I know about the particular setting that. Okay. Any other stuff there?
No.
Okay. Let's see some of the insights. I'll try to squeeze into 5 minutes, 10 minutes before I wrap up. So let me just kind of some observation on how do we get about this kind of result. So first, let's take like maybe two aspects on the matter. So first, in the limit, right, GD, when we run for many steps, we get ERM, some ERM, right? And we already know, I told you, we as a community already know that ERM fails in this case from this SSSS paper, stochastic convex optimization. So we expect this kind of construction or argument to be helpful, right? But one thing to kind of be careful about is that we also know that SGD is going to converge to ERM, right? Actually in the same rate, right? So we need to be careful. It's not like a black box argument. And we are also not interested in, of course, in the limit, but kind of in a finite time result, of course. But I think the more worrying thing is this: everything will apply equally to SGD, right? Another thing to note is that if the loss is sufficiently smooth, meaning that the gradient is a Lipschitz operator, it's kind of right. It doesn't have corners. Smooth in the classical optimization sense. Then we know from this train faster generalized better paper, or kind of variation of it, let's say, that gradient descent is stable as an algorithm, and therefore it generalizes. We have a kind of a very good understanding of why stability implies generalization. And we can show that if the loss is smooth, then the algorithm that we care about now is stable and therefore generalizes. Okay, what is stable? Let me just say very roughly what is the idea behind stability. So I'm thinking about a learning algorithm as delta stable, let's say, if replacing one example in the sample, in the input to this algorithm, changes the output by delta. Okay, so the output for GD is this W bar that we seen before, right? So if W bar changes by delta, subject to one switch of one example in the sample, then I'm going to say that this is a delta stable algorithm. And indeed, if the loss is smooth, we have such a result. And as I said, there is a very general kind of understanding that the stability implies generalization in this sense. So delta stability implies delta generalization, O of delta. Okay, so if things are smooth, sufficiently smooth, then we are good. Okay, so we need to be careful not to go too much into the smooth territory. Okay. Yeah. So let's see why ERM fails. And this is a very, very simple construction, from this SSS paper. Yeah, so very simple stuff and very nice. Let's see. So I'm going to construct a sample, right? So we have a data point Z1 to Zn and D dimensions, okay? And I'm going just to kind of pick uniformly at random either 0 or 1 to put in the ith feature of each data point, okay? Just uniformly at random. And the thing to note here is that if the dimension is large enough, exponential in the sample size, unfortunately, but this is why this argument is so simple, I guess, because it can go to arbitrary dimension pretty much. Then with nice probability, let's say at least half, we'll have a column which is all zeros. Okay, this is very easy probability, one-on-one probability to show that. Okay, so again, if the dimension is large enough, we're going to have at least one column with of this kind with nice probability. And then let's look at this loss function. Okay, so this loss function just takes the squares of sum of squares of the features of W, and the coefficients are these numbers. Okay, the sample, the feature vector. Okay, we can show that it's convex and Lipschitz. It's straightforward. And let's see. So first, if we have this kind of column and we look at the standard basis element EK, this is the kth column, let's say. Okay, so EK is going to have 0 empirical risk. Okay, because everything here is 0 and everything becomes 0 in the empirical risk. Okay, so this vector has 0 empirical risk, but unfortunately, it's going to have a constant test loss, just because, right? We picked a 0, 1 with the probability half, so the empirical risk, sorry, the test risk is half, right? That's it. So it's going to be half regardless of anything, and the empirical risk is going to be 0. There is a gap. This is basically the idea. Very simple stuff. Okay, ERM is going. Some ERM are going to fail. Some ERM are going to work. For example, 0 is a great ERM, but we are going to pick the bad one in purpose. Okay. So does it mean that GD is going to fail on the same loss? So unfortunately, we already know that there is another thing to verify, right? So if we initialize at 0, then we're going to get stuck at 0. So we need to take very minimal care. More generally, we already know, I already told you that if, actually for this loss function, GD is stable and therefore it generalizes. So there is something else that we need to take care of. And basically, we need to kind of push away GD from 0, to tilt it from 0, kind of make it move far away, but in the direction that we want, in the direction of a bad minimizer. Okay. Okay. So actually, tilting is also tilting away is also not very difficult, and it's actually been done last year by this Vasily et al. Paper that I mentioned earlier, and they showed basically an example that makes GD unstable. Gradient methods are unstable pretty much. Okay, so basically a lower bound on the stability of the algorithm. So what do we see here? We see here kind of a loss function that for one sample, one possible data point, it has a negative slope. Okay, this is the ones vector. Okay, so we have kind of a slope of minus gamma. In all of the directions. Okay, so think about gamma is arbitrarily small, like machine precision number. And otherwise, we have this maximum of all the coordinates and maximum with 0. Okay, let's look how it looks something like this. Okay, at least this function looks something like this, right? In each direction, we have kind of a hinge. Okay, now I want to claim that kind of this makes things unstable. So I'm going to show you that having Z0 in the sample or not having it in the sample is going to produce very different results. Okay, so let's look at two cases. First, Z0 does appear in the sample. Sorry, doesn't appear in the sample. In this case, we don't have this at all. We have only this function. Okay, So it looks precisely like this in each direction. And what happens for GD? What's going to happen? Right? It has zero gradient at zero, right? So it's going to get stuck at zero. And if you're worried about subgradients and kind of not well defined, so we can move it a little bit, right? I mean, we actually do it in the proof, but forget about it. We can make the gradient kind of well defined, kind of uniquely defined at zero. So it gets stuck at zero and doesn't move at all. Okay, this case is easy. What about the other case where a z0 does appear in the sample? Let's say it appears once, okay, for simplicity. So we have this kind of function, right? Some negative slope up until zero, and then this hinge again. Okay. So what's going to happen now? We are going to move away from zero because we have a gradient, right? So we have some gradient which is a negative in all entries because of this negative shift. Okay. Doesn't matter about this. It's just that negative. So the next iterate is going to be positive in all of its entries are going to be positive. Okay. So this kind of red dot over there. And now, thanks to this hinge function, we are going to take a gradient step with a huge gradient, right? So we've been tilted away from zero, like in very, very small, like this gamma, think about it as a very, very small number. So we just moved a little bit away, but now we have a huge gradient moving us in the other direction. And we're going to move roughly eta, okay? The step size times the gradient, okay? So we're going to get to minus eta after this step. Okay, so the first coordinate that we get from this maximum, right? Take one maximal coordinate, take a gradient step, we're going to get minus eta in that coordinate. And we can show that repeating this process will actually give us minus, we actually going to get each time a different coordinate, and we're going to sum kind of, after t steps, we're going to sum t different coordinates. Each of them is going to be minus eta. Okay, so what did we get? We get that in the two cases we got the very, very different points. In the first case we got zero as an output. In the other case we got a point which is something like eta root t away from the blue point, from zero. So right, changing one sample in the training loss kind of got us very far away from in the two cases. Okay. So let me get to the main thing here is that we basically, ideally, we want to put two things together, right? We want to show that we are being pushed away from zero in the direction of the actual, in the direction of the bad minima. Okay, so kind of the most simple idea would be just to mix everything together, right? Take this bad ERM function and this unstable stuff, instability stuff, add them together and hope for the best.
This is dependent only about the number of steps, right?
Sorry?
This is dependent only if you bound the number of steps.
Sure.
Okay.
Yeah. Instability will only be worse if, instability actually works in the other direction. The more steps, the more unstable. Yeah. Okay. Okay. Yeah, but it will work for any number of, as I said before, for any t and for any eta, you'll get the result in sufficiently large dimension. Okay. Yeah. Okay. So let me say, just say for this. Okay. So yeah, we want to put things together. Let me just pick what I want to say in the short time I have. So yeah, so the idea here is that we are going to pick the dimension large enough so that we have a t of those bad columns, right? Bad columns means something that we're going to have a generalization gap. Okay, so picking larger dimension will allow us to have like t of those, and now we can use the same argument as before to show that we are moved away by the last term there from zero. We are being tilted away from zero in all coordinates. Okay, so this is kind of the plot of each coordinate in W. Okay, so we are being moved to the positive orthant in all coordinates. But unfortunately, the next step is going to use kind of this hinge is going to pick kind of the maximal coordinates arbitrarily, right? So let's just in kind of in serial order. We can break ties more cleverly, but let's say just break ties arbitrarily. So we're going to just to pick coordinates to kind of kind of right to do gradient step on. And unfortunately, after t steps, we are not hitting enough of the red guys. We want to hit many red guys to get generalization gap as large as possible. Okay, to get kind of the worst thing. Okay, so this doesn't quite work. Actually, yeah, I want to say that this actually we have a even worse behavior, because this additional guy that we added actually pushes back coordinates to 0. Okay, it has also gradients that push us back to 0. So anyway, but the red guys are still there, but not enough of them. Okay, so the idea is just to correlate between the tilt from 0 and the bad coordinates. Okay, so we can show, and I'm not going to show because due to lack of time, but we can show that a more clever choice of this tilt vector here and arbitrarily small gamma again will do this push only to the coordinates that only the red coordinates will be positive and the others will be negative. And we can do the same simulation and get like all the red guy. After t iterations, we get t of them. Okay, so it kind of cherry picked the bad coordinates and move them away from 0. And if we sum the kind of the contribution of all these coordinates to the generalization gap, we get something like eta squared times t. Okay, which is order of 1 for eta equals 1 over root t. Okay, this is slightly worse than what I claimed before. Just for simplicity, we can actually get this under a square root in a kind of a bit more technical analysis. Okay, maybe one thing that is nice to see is how SGD is avoiding this, right? I mean, what's going on? So, so the thing is that this tilt vector there, only if we sum everything together, it will kind of push the bad coordinates away. If we don't sum and just pick one of them or uniformly at random, we are going to the coordinates that are going to be pushed into positive direction are going to be just those that have 0 in the corresponding feature vector. Now, these are uniformly at random, right? So half of them are going to be positive, half of them are going to be negative, right? I mean, the red guys are going to be positive, but among a lot of other guys. And now we lost kind of this cherry picking mechanism, right? So SGD kind of avoids it just by sampling and not summing up the gradient, basically. Yeah. Pretty amusing to see that. Okay, one last thing, and then I will summarize. Is it okay to kind of still a few more minutes? Okay. So back to this question of regularization. Is regularization key, right? I mean, we have one thing unsettled. We've seen that this regularized ERM, so SGD, we know it sucks. But what about this regularized ERM that I showed you earlier? It seems that regularization is everything. Right? I mean, it works. I told you it works. I didn't show you show you the proof or the kind of the claim, but it's optimal. So what's going on? So let's take a slightly closer look at this algorithm, and let's look about the kind of the work that we need. So this is kind of our abstract minimization. Let's work it out. Let's see how many actually gradient steps do I need to do on this minimization in order to get this W bar, sorry. Okay, so this is kind of well known even from this earlier paper that if we want to get so if we minimize this regularized objective to within some delta, okay, so then the generalization error of this mechanism will be something like root delta over lambda. Okay, if we minimize it precisely, this will be 0, and we'll get kind of yeah. There is plus. Yeah. Okay. Forget what I just said. It's a bit more complicated than that. But yeah. But this is how the up to other terms. This is how the test error is dictated by the empirical suboptimality. Okay. This delta. Okay. So what do we need to do in order to generalize? If we want epsilon generalization, we need to solve this up to within lambda times epsilon squared, and plug it there, and we get epsilon, right? Now, it's a very, very short computation, which I'm not going to show, but if we choose kind of the parameters the right way, we choose lambda the right way, and we take epsilon to be 1 over root n and optimize everything and use kind of the best possible gradient method to solve the internal minimization, we get again that we need n squared iterations, even with this algorithm, okay? So if we work out the number of steps, you get the same result as GD. Regularization doesn't help even here. Okay, this is I think one of the things that most surprised me. I wasn't ready for this. I thought that this is a great algorithm, but turns out it's not that great. Equivalent to GD, basically. Okay. This is right. Good question. This is not lower bound, and we have a result that's showing that this analysis for regularized ARM is optimal in that paper. In the paper I was talking.
In the lower bound for this.
Yes, for this setting of 1/√n and fixed learning rate and
regular.
Yeah. We show that this cannot break this 1/epsilon force barrier. Of course, we can do better with SGD, right? It's not a kind of information theoretical lower bound, it's a lower bound for this algorithm. In fact, in a more recent paper, still not online even, we show more stronger result. This is a paper with, again, our PhD student Idan Amir and Yair Carmon from our department. Again, if we take dimension large enough, then any algorithm that uses full batch gradients, so forget about GD. If your only access to the sample is using full batch gradients, you're not going to break this barrier. Okay, so for any algorithm, randomized, deterministic, whatever. Okay, you'll need at least 1/epsilon to the 4 steps. Whereas SGD generalizes doesn't care about dimension, doesn't care about anything, right? So this is kind of the full batch thing is what kills us. And recall that this is matched by you're not listening to me, right? Recall this is matched by GD with small enough step size and enough iterations by this Basili et al. Nice result. Okay, I think I said everything. It turns out that SGD generalized better than GD, and regularization doesn't really help the algorithms, somewhat surprisingly to me at least. Stochastic training was kind of the main thing, at least from this aspect of this talk. And many questions are still, we still don't know how to, many kind of variations of the setting are still open. I'm happy to talk about offline, and thanks for listening.
Thank you.
Time for more questions?
Here from the
We can now actually turn on the volume. If we need to.
Okay, no questions.
Okay.
So thank you again, and
thanks.
great talk.
It was fun giving live talks again.
Yeah.
We should do that more often. Thank you.